Thank you very much, Lute. Lute knows me well. She knows I have a reputation for running out of a conference before it's finally over. She figured out a way to take care of that today. So she scheduled me last so I would stay for the entire show. So before beginning today, I want to make just a couple of comments. I appreciate very much the education that I received here at the University of Michigan, and especially appreciate the various faculty members that I took courses from and that influenced me so greatly. I was pleased yesterday to see Borchardt, Jack Borchardt and Jean Glisson honored with the faculty scholar that Tom and Greta Newhoff set up. And I thank you very much for that. Jean Glisson in particular has a very soft spot in my heart. My association with him goes back to 1958. I graduated from high school. I was taking a route surveying course sponsored by the Michigan Highway Department. This course was being taught by Jean Glisson. Jean stopped by my drafting table one day during a problem session, and he said, "What are your plans for college?" And I said, "I don't have any. I'm going to work." He said, "You should think about college." So to those of you who are going to be faculty members, sometimes students will listen to a professor. So I listened to Jean. I'm glad I did. I came to the University of Michigan in civil engineering. I wasn't quite certain that what aspect of civil engineering I wanted to specialize in. I took a course from Jean, and I, together with several of my colleagues, fellow students, Tom Kyneth, John Schenk, Denny Hirota, to name a few, Jerry Fess, names that some of you may know. And I took that course, and it convinced all of us as a group to move on into graduate studies in environmental engineering, sanitary engineering at that time. Well, enough of that. I was hoping to see Jean here today. Unfortunately, I'm told that he's fighting cancer and is not moving around very well these days. So we wish him well in this battle with cancer. My presentation today is a little bit of looking back at where we've been and a bit of looking forward, what we might anticipate in this area of water quality control, water treatment. Acknowledge my co-author, Ana Martinez. She was a PhD student at the time at the University of Illinois, and she helped me put this presentation together, so I appreciate that. So it's major advances. Let's think about that for a moment. When we think about water treatment, like me, it's going back, say, 4 decades, what kind of changes have there been along the way? Well, what is a major advance? Well, you can think in terms of number of entities now using it. 4 decades ago, some of the things that I'm going to talk about were not being used. Beneficial results. If it's going to be an advance, it's got to do something good for us. And then I would note that, and this is a little bit consoling, I think, for all of the researchers in the audience, this incremental research is so important. All of us like to dream about coming up with this one major advance that just makes a tremendous change in everything that is going on. Everything is different because of my research. That doesn't happen very often, and more commonly, it's the incremental research that gets us to these major advances. So certainly, I think all of us would put membranes and membrane processes on the list, our list of major advances. The synthetic asymmetric membrane was developed by Snoeyink and co-workers at UCLA in 1960, a lot of years ago. Many subsequent advances, many developments of new membranes, module configurations, different types of membranes, microfiltration, ultrafiltration, nanofiltration, a lot of studies of pre-treatment and post-treatment to prepare the water for the membrane process, to prepare the water for distribution after treatment, and energy efficiency. All of these factors came into play. So take a look at this first graph down in the, on the lower left. Reverse osmosis capacity versus time. 1960, this major advance took place, development of the membrane. By 1980, there probably weren't very many people around thinking that this was a major advance. It took us many years, decades, of our incremental research by many different people to develop reverse osmosis to the point where it's a very commonly used process today. So this capacity, 60 million cubic meters per day in 2010, and we're on a very fast slope of increase. One of the reasons that it was not very commonly used is this issue of how much energy does it take. So it's on the right-hand side, we see the bar graph where it's 1970, 12 kilowatt hours per cubic meter. Now this has come down over the years to about 2, but 2 is, it's a little bit loose because that number depends very much upon composition of the influent water and especially on the amount of recovery. But that energy efficiency increase was so important in causing membrane processes, development of membrane, to be something what we call today a major advance. Just an example of a desalination plant in Barcelona, Spain, the Bochardt Valley plant it's in, near Barcelona. Notice that the reverse osmosis is those 2 units about in the center of the diagram up towards the top. Coming into that plant, we have the intake, we have flotation to remove solids, we have gravity filtration to prepare the water for reverse osmosis, we have microfiltration to prepare the water for reverse osmosis, then the RO units themselves, and then a remineralization step where you put alkalinity and calcium back into the water to stabilize the water for distribution. Then, of course, we have all the effluent treatment. So if you look down in the box, the red box, 3 kilowatt hours per cubic meter for their recovery of 45% recovery from ocean water, and another kilowatt hour per cubic meter for the pre-treatment and post-treatment. So the entire system is up around 4. Now it's membrane filtration capacity versus time. Membrane filters have really taken off, but it all goes back to this 1960 when the asymmetric membrane was developed. But you see membrane filtration had to have some developments along the way. We needed to develop the filtration membrane, the ultrafiltration membrane, and that really did not take off until I left my glasses off. It looks like about 2005. So you can see how it's taken off since that time. Membrane filtration for municipal application, desalination applications, pre-treatment for RO and desalination, and industrial applications. So certainly, membrane filtration is an important tool for us today. The membrane bioreactors Tom Newhoff says his firm just designed 3 relatively recently. They're operating, working well. So 2015, it's estimated that there's $600 million per year that will be spent on putting membrane bioreactors into place. And you can see that yearly amount spent on membrane bioreactors has been increasing rapidly as well. I would put UV disinfection into the category of a major advance. Drivers are the protozoan cyst waterborne disease outbreaks. And toxicity in the secondary effluents. This toxicity is introduced by chlorination. So we produce a residual chlorine, important for us in distributing drinking water, but certainly in wastewater, we don't want to kill off those aquatic organisms. So these were the major drivers. UV capacity versus time, you can see how that's been increasing. 4,000 North American wastewater plants used UV in 2008. So since that came into play, since we first started using it, that really has taken off, especially for wastewater disinfection. But certainly also we're seeing it more and more commonly in our water plants as well. I would include ozonation on the list of major advances. Certainly in the United States, we were slower to pick up on ozone than the Europeans. It's used for so many things: taste and odor, disinfection byproduct control, disinfection, synthetic organic compound oxidation. It can be used as a coagulant aid for some waters. And certainly can be used to remove color. All these applications would say we should be seeing a lot of it, certainly if ozone systems can be made to operate well, and I think certainly the engineering is in place for that. There's some deficiencies. For example, if there's bromide in the water, you can get bromate, and that of course is a regulated disinfection byproduct. And certainly also you can generate the biodegradable organic compounds, the assimilable organic carbon, and if that is generated in order to prevent biofilms in the distribution system, we better have a biological stabilization step in our water plant. But ozone water treatment plant use, 4,000 plants worldwide, 250 in the United States right now. Now, drivers for change. Let's spend a little time on that, and I would like to address this really in 4 categories. I'd like to take a look at what regulations can do to cause change, bring about change. Water availability, quantity is so important to us. Energy considerations, and then I would like to end with the discussion of distribution systems. So it's the regulations, first of all. Let's take disinfection byproducts as a case in point. With disinfection byproducts, of course, we have our THM standards, 80 parts per billion for THMs and 60 for HAAs. Fairly complicated wording in the law, but essentially these numbers are firmly in mind. Nitrogen, 1 ppm. Now these levels are very important, especially the nitrite. Then we also, in our surface water treatment rule, we require a measurable disinfectant at the tap. Okay, so what has this caused? What has this brought about? Monochloramine for secondary disinfection. So about 1/3 of our utilities now use monochloramine. What is the downside? Well, it's possible to have nitrification. Monochloramine breaks down into ammonia when it is chemically reduced by materials on the pipe wall or organic matter, different inorganic substances. So the ammonia can now be converted to nitrite and then to nitrate. So about a third of the utilities that are using it, so 1/3 and 1/3, about a third of the utilities that are using monochloramine have nitrification problems. And these can include dissolved oxygen loss, chlorine loss, an increase in nitrite. We don't often go above that 1 milligram per liter nitrite nitrogen, but certainly we see the nitrite coming close to that in a lot of cases. And certainly an increase in metal ion release from the scales that build up in our distribution systems. All of these can come about. Now, Larry Sanford here from Ann Arbor is saying, wait a minute, Verns, Ann Arbor uses monochloramine just fine. So it's certainly 2/3 of the utilities that are using it use it just fine, and it's working well, and it keeps THMs down. But there are many that aren't doing that, and from my perspective, if there's a regulation that is put in place that causes 1/3 of the utilities that are going to make adjustments to meet this regulation, I would not put it in the category of a major advance. It's a major change, but it's certainly not a major advance from my point of view. Now, what's the alternative? The European Union has a standard for nitrite nitrogen that's about 6.5 times more stringent than our standard. The net result is that if they try to use monochloramine, I was involved in one study where this was attempted, and it's a short distance out of the plant into the distribution system, the European nitrite standard was violated. Okay, so there's a strong disincentive there, the European Union standard, to not use monochloramine for this reason. Another important factor there is that they're not required to have chlorine residual persist to the tap, and their standards have led to a much greater emphasis on in-plant treatment. Now, we saw an example yesterday from Cincinnati Waterworks where they were doing a very good job of in-plant treatment, but they had a little extra stuff that they had to do in order to keep these THM regulations under control, the presentation of Mr. Froome. Certainly water shortage is a driver. We've heard this before from our speakers yesterday, particularly the Borchardt lecturer, George Trebenaglos. Poor quality supplies require better treatment. We go to direct potable reuse. Certainly, if we're using sewage effluent as our source of water for potable use, would say we better be very certain that our treatment is in good shape and with a good, robust system. Certainly, there's increasing amounts of treated wastewater and urban runoff going into our water supplies. And a very nice report on this is the first reference there, the NRC report, National Research Council. This committee was chaired by Rhodes Trussell, and the report was published in 2012. Outstanding report on the potential roles for water reuse, including direct potable reuse for supplementing our water supplies. I recommend that report to you. It's available free of charge on the NRC website. There's a little more details in the reference list at the end of my presentation. So it's water shortage versus treatment. Certainly, RO is attractive as a barrier. We would like to have a complete barrier, reliable barrier in between us, the consumer, and this poor quality of supply that we're going to take and treat. So RO is very attractive in this respect, and it's being used very effectively for this purpose. But this business of inland concentrate disposal is a really serious problem for us. We heard from Professor Ellis about deep well injection. Certainly deep well injection is a possibility for us, but this is not possible in all areas because of the unsuitability of the places where you might do the subsurface injection. Zero liquid discharge is a term that has come into our nomenclature in the field. Zero liquid discharge means take all these salts that we're taking out with something like reverse osmosis, take all these salts and make them into a dry cake. If we don't go all the way to zero liquid discharge, another term that's coming into play is near zero liquid discharge, where we work very hard by different treatments to get the recovery up to 95 to 98%. Now, this to me is a very exciting area of research because it involves a good process knowledge and application of some good solid water chemistry. Zero liquid discharge, you would produce a cake like that's shown in the bottom picture there. What I'd like to do with zero liquid discharge is to give you a little bit more of a picture about this. There's a 0.14 MGD system that's now being constructed in Pueblo, Colorado. This isn't a drinking water system, quite far from it. The United States still has stockpiles of chemical warfare agents. International treaty, 98 countries or something like that has signed this treaty. The U.S. is one of them. We've got to destroy these weapon stockpiles. One of these stockpiles is in Pueblo, and there's a zero liquid discharge plant that's being constructed now to destroy these chemical weapon agents, so nerve gases, mustard gases, things of that sort. You can go online, by the way, if this intrigues you. You can go online, just Google Pueblo and chemical weapons, and you'll get some very nice videos of just how this destruction is taking place and just how this plant is being run. Okay, but what is being done there? Well, it's the same thing that's going to be done with the chemical weapons materials from Syria. They're going to take it, in the Syria case, they're going to put it on a ship, they're going to raise the pH, high temperature, they're going to hydrolyze that material. They do the same thing here at Pueblo. They're going to do the same thing. That by and large destroys these compounds. So high pH, chemical hydrolysis. But then you're left with a high concentration of water that may be contaminated. Nobody is ready to put it in the aquifer for drinking. Nobody is ready to send it to the water treatment plant still. It's highly politically charged. Okay, so what are they going to do with it? Well, to go through a bioreactor. Fixed film biological process, first of all. And then I was not involved in the design of this plan. I'm involved in an oversight committee to see how things are going. But I would put in reverse osmosis before evaporation in order to recover as much water as you can before applying heat. The minute you start applying heat in evaporation steps and crystallization steps, you lose a lot of energy. In this particular case, bioreactor, straight to evaporation, then to crystallization, then to a belt filter to create a dry cake. This is just a brief sketch of the flow diagram after the water is treated by this biological reactor, the bioreactor, fixed film biological reactor. You drop the pH, put it through a deaerator, and you take off the CO2. Okay, that's so that you can go to evaporators and get a high concentration. You go raise the pH, go into the evaporator. Now this evaporator is a real monster. 596 50-foot long tubes. The water is applied to the top of these tubes. The water flows down the inside. It's heated from the outside. And you recover a lot of the water that way, and you produce a distillate, which you recover, put it through a carbon filter, reuse it in the plant. The concentrated brine you take to a crystallizer. Control the pH, go into a crystallizer, and convert your salts to crystals, salt crystals, sodium chloride, whatever types of salts are present. Then go to the belt filter for solid liquid separation to produce, hopefully, that dry cake that I showed you on a previous slide. There's a number of questions. I hope we get that dry cake. Probably the cost of this plant as built will be on the order of about $2 billion. Okay, so $2 billion is on the order, what did George Tribunagos tell us yesterday? $6 billion will give us double reverse osmosis at all of the wastewater plants in Southern California. That's not too much more than $2 billion. So in here we've got 0.14 MGD. So it's definitely DOD is throwing money at this problem. And a big reason is political sensitivity. Why are they using this? Well, some very influential congressmen live in Colorado. The other stockpile is in Kentucky. There's a very influential senator in Kentucky that has a lot to say about how and what is going to be done. Near zero liquid discharge, RO and water reclamation, bioreactor effluent, primary RO, and concentrate treatment. Okay, so if we're going to do this, we're going to treat the concentrate to get our recovery up to 95, 98%. So if we just do primary reverse osmosis, the way that Orange County is doing, or the way that they're doing in Singapore today in their reclamation systems for biologically treated effluent, recoveries are about 75%. You can play with that number a little bit. Okay, so there's stuff that we've got to do to that concentrate to get some more water out of it. And the kind of processes that we're talking about are lime softening and pellet softeners or seeded precipitation, cation exchange, electrodialysis, a fancy version of electrodialysis metathesis, ozone, biologically activated carbon, capacitive deionization, and secondary reverse osmosis. There's lots of different processes that are coming in as alternatives, and a lot of these processes need further development for this kind of process. But, and this is a big but, if we get our recovery down to 95%, if we have a 1 MGD plant, we have 0.05 MGD of concentrate that we still have to dispose of. And that's still a pretty big disposal problem. So it's, our problems haven't gone away in any respect, but we certainly have made them smaller. So if we talk about concentrate disposal, so the scenario is that we're going to do everything we can to reclaim all the water we can, to reuse all the water we can from in our sewage treatment plants, effluent treatment. We're going to recover as much as we can. We've got this concentrate problem. I raised the question as to whether or not we really need RO. Maybe we do if we're going to drink it, if we're going to drink the product. But if we're not going to drink the product, and there are lots of other uses for water in a city, in a municipal area, there's lots of other uses for water, What can you do with ozone, biological activated carbon, or the advanced oxidation process, O3H2O2, hydrogen peroxide, and biologically activated carbon? 2 papers were published here that I referred to that did a beautiful job of taking out a lot of these endocrine disruptors, the pharmaceutically active compounds. They came out of this with a pretty decent quality of water that could be reused in many situations. Now, we need to address this issue of, is it a robust process? Robust enough so that now we can go to put it in to a drinking water system. But certainly, I think there's a real use for this kind of water. So maybe we don't have to put everything through a reverse osmosis system. Excellent trace organic removal, but we'd raise the question, we need some good municipal-wide planning studies to see how these waters of different qualities that we can produce most economically, how these can best be used to optimize our needs for, give us the water that we need and minimize the energy and cost. Certainly energy is a big consideration. We've heard about that from various speakers. Reverse osmosis for desalination. One of the things that I do periodically is go to Singapore and get involved in evaluating research that's being done there. The Public Utility Board in Singapore funds a lot of research. One of the projects that they, well, one of the requests for proposals, I should say, that they put out, a challenge proposal, they said, look, we've got reverse osmosis, we're reclaiming water, we're taking it, putting it in our drinking water reservoir, we're using this water for industrial purposes, but we're spending 3.5 kilowatt hours per cubic meter in energy, and that energy cost is important to us, so how can we reduce that? So let's have a challenge proposal, a challenge RFP, to see if we can cut that in half. 1.75 kilowatt hours per cubic meter, including pre-treatment and post-treatment. Okay, keep in mind this Barcelona system, which was at 4. Okay, so the proposals came forward for that, and interestingly enough, Siemens won this grant by proposing a system involving ion exchange, electrodialysis, and electrodeionization. And electrodeionization is just electrodialysis with some ion exchange resins put in between the membranes. They were able to get very close to this 1.75. So if this energy is really very important, if this energy issue is very important, we may be able to use something other than reverse osmosis. We're still concentrating the salts. We still have salt to dispose of. So we're taking the salt out of water, so we still got to get rid of that salt. So we didn't completely eliminate that problem, or Siemens didn't with this particular patent. Recovery of energy from municipal wastewater. So we heard about some very interesting research going on here, and very important research under direction of Lute Raskin and co-workers. Anaerobic membrane bioreactors. And the idea is that if we use these in place of aerobic treatment, the activated sludge process, we'll be able to reclaim energy much more efficiently. One of the processes that I like very much in this regard, a competing process with Professor Raskin's is, and co-workers, is that of Perry McCarty, who has proposed taking membrane fibers, the immersed membranes, so the Z-weed from xenon or something like that, and immerse it into a bed of activated carbon that's fluidized. So the fluidization, the granular carbon is slowly moving up and down over these ultrafiltration fibers, and it's cleaning that membrane. Okay, so the net result is a very high flux. If he takes the fibers, that ultrafiltration fiber, out of the fluidized activated carbon, flux drops off immediately. So he gets some very nice flux in that operation. And then that is being used at different locations in pilot facilities to treat raw municipal wastewater without any pre-concentration at ambient temperatures as low as 5 degrees Celsius, and getting excellent removals in that operation. So the activated carbon holds the biofilm, and the ultrafiltration membrane then prevents any passage of microorganisms into the product water. I think we're just getting off the ground for this. You know, if you think about all of the activated sludge plants that we have around the country, how can we convert those from a high energy user that we've got to something that gives us a good yield of energy? So how can we take these activated sludge processes and convert them to a nice anaerobic system that operates, that treats raw wastewater? That's a challenge that's in front of us, and I'm glad to see the folks here at the University of Michigan heavily immersed in that operation. The last thing that I wanted to talk about is the distribution systems. The distribution systems as a driver. There's a lot of things about distribution systems that we don't understand. We heard some excellent presentations here at this conference about microorganisms and distribution systems. And I would support that research. I'm pleased to see it and encourage further research along those lines. Now, let me give a couple of examples. Okay, so the critical issue is how should we treat water for distribution? On the left-hand side, lower left-hand side, is a picture of manganese. A manganese deposit. This is a deposit that happens to have been in the Hanover, Germany distribution system. Walter Kohle took a picture of that, and it's a very nice picture, so I put it up here. But manganese. Manganese, the secondary MCl is 50 micrograms per liter. But if you have 40, you meet the secondary MCl. If you have 40 or 30, and you go into a distribution system with 40 or 30, you probably are going to have black water problems at the tap. Manganese builds up in the distribution system and periodically releases. Now, the release, hydraulic factors are certainly involved in this release, but I think microorganisms are also. So in a picture like that, we'll probably have manganese in a +4 oxidation state, so MnO2, or something very close to the +4 oxidation state, which is pretty stable, but manganese-reducing organisms can convert that rapidly to Mn+2. And Mn+2 is very soluble, goes out into the bulk water, gets reoxidized, and carried to the tap. The second picture here is one of the online cast iron pipes. And you say it's, online cast iron pipes, nobody is putting those in anymore. I agree with that. Nobody is putting in online cast iron anymore. But about 50% of the pipes in our large cities throughout the United States are online cast iron pipes, heavily corroded like this. And knowing how to distribute water without having iron release from these scales is very important, because these can be the cause of a red water problem. They can also exist in a pipe and not cause any problem at all. I think microbes are heavily involved in affecting the release of iron from these scales, and My research group and I have done quite a bit of research in this area, but none of it has been in the microbiological area. That's why it says the microbes are too tough to handle. So I'm leaving that for all of you microbiologists. But I realize its importance, and I would encourage you to take a close look at how do you control the microorganisms in a system like that. Lead pipes are over on the right-hand side with scales. Now, it's lead pipes, lead scale. Okay, so if you think about water at a pH of 9, it's 9.1, 9.2, that scale will be lead carbonate, lead in the +2 oxidation state. If you are feeding orthophosphate, you'll have a lead scale. You'll probably operate in a pH range about 7.5 to 7.8. It's an optimum range for you. You'll operate in that range, and you'll have a nice lead scale, Pb in the +2 oxidation state. If you use free chlorine, and it's a good reason to use free chlorine, and Cincinnati is using free chlorine, I suspect that they're getting lead in the +4 oxidation state. So some of these pipes here have a little bit of a reddish color to them. That's the color you would expect if you have PbO2, lead in the +4 oxidation state. But if you take a careful look at the analysis of that pipe, there's iron in there, and there's manganese in there. So if we say lead in the +4 oxidation state, that can be reduced. Iron in the +3 oxidation state, that can be reduced. Manganese, it can be reduced. So if there's stagnation in premise plumbing, such that you lose oxygen, okay, you have a condition at the pipe wall where the microorganisms, manganese-reducing organisms, iron-reducing organisms, can take these materials and release iron and manganese. It won't be much, but there's good evidence that it takes place. It leaves the pipe, goes out into the bulk water where there's a little bit of oxygen, gets oxidized, and now you have a manganese particle and an iron particle that does a very good job of absorbing lead ions and carrying the lead ions to the tap. Okay, there's a role of microorganisms in lead release and lead scale that we're just beginning to understand. It's an important role. So certainly the lead 4 to lead 2 situation, Washington, D.C. found out all about that and found they had lead 4. They went to an oxidation reduction potential where lead 2 was a stable form, and they had tremendous lead problems resulting from that. It was a situation that was preventable if we had understood the chemistry before. We could have prevented it just by having some orthophosphate in the system when we made that conversion. What was the conversion? It was going from free chlorine to monochloramine. That lowered the oxidation reduction potential. It made the lead 2 the stable form instead of lead 4. And lead 4 is very insoluble, but it rapidly converts to lead 2. And lead 2 was much more soluble than lead 4. So they had a tremendous problem resulting from that. Okay, so there's been lots published on that, but certainly I think in all of these situations that we're talking about here, except the lead 2 to lead 4, microorganisms could play a role. We need better understanding of the chemistry of those scales to better understand how to treat water for distribution. So a couple of final thoughts. So we certainly have major advances that have changed the way we treat water today, without question. There are drivers that are going to force us to do things differently, and some of those drivers, like regulations, may drive us in the right direction, and some of us in a direction with unintended consequences that will create some problems for us. From my perspective, this is certainly an exciting time to be a researcher in the field because all of these areas give us lots of things to take a look at. Okay. Thank you very much.